Hi, everyone. Thank you for joining this webinar. Hope the audio is okay. If you have any troubles, please let me know. So this is part of a series of webinars that we're giving. This is the last one for the year. We'll be giving more next year. The topic for today's webinar is using computational fluid dynamics modeling for particle technology and process development. A few housekeeping items before we get rolling here. We've muted all participants to ensure that there is no background noise. To ask a question, please use the chat or raise your hand and we will address it. Please let me know if there's any other issues such as audio in the chat. We're using the Q&A. This presentation will be recorded, and if you have any trouble, please contact Karen Manning, whose phone number can be found here, or you can use her email. To start off, I want to introduce the firm for which I work, Verist Engineering. So Verist is an engineering consulting firm based outside of Boston in Massachusetts. We're been around for a while, founded in 2006. We're currently 12 technical staff, 80% of whom have PhD plus level education. We provide multi-physics simulation services and mechanical testing services for industrial clients. So in addition to our compute, we also have a 3,000 square foot mechanical test lab that's based in Needham. As part of our practice, any of our branches, we transfer all methods, models, and data to our clients. All of our clients own the intellectual property that's generated as part of projects. The examples I'll be showing today do not fall in the scope of any client projects because we take confidentiality very seriously. Our tagline is that we provide academic level expertise, but on an industrial timetable. So this differentiates us from much of industry as well as academia. Our practice areas I've highlighted here. So we do a lot of materials engineering and mechanical testing. My practice area falls under the scope of multi-physics simulation using computational fluid dynamics, transport phenomena modeling, and other types of models. We also do a bit of legal work via failure analysis as part of our practice. We also define ourselves based on our subject matter expertise. So I'll introduce mine in a moment, but here I'm just showing the broad array of subject matter that we cover at Verist. Not only fluid mechanics and heat transfer, but a variety of multi-physics coupled to these processes, electrochemical and chemical reacting flows, low frequency electromagnetics, material science, structural mechanics, among other topics. So all of these areas fall within the scope of our practice, and this is why our clients tend to come to us when they get stuck on difficult problems. I won't go over all of our staff, but I've just decided to highlight some of our staff examples here. So these are all our members who are expert in fluid dynamics, modeling at all length scales. I've highlighted myself. So my name is Joe Barakat. I'm a PhD in chemical engineering. My background is in microscale flows involving particulate processes and or chemical or electrochemical reaction. A lot of the problems I work on for industrial clients span pharmaceutical sector, the energy sector, basically involving complex fluids that interact with molecular materials in some way via complex couplings. So having introduced ourselves, I wanted to motivate the topic for today's webinar. Again, the topic is on particulate flows in liquid media. So the first question is, why would we care about this topic at all? And if you're attending this webinar, you probably already have an answer in your head. Particulate media are present in a variety of different applications, both in industry and science, but also in the household. One example is in any catalytic reaction that involves fixed bed reactors. The properties of these reactors depend sensitively on the bed microstructure, and that's important in their design. In the lab, you frequently encounter particulates in the form of powders, and also in analysis, such as in chromatography. A variety of products, such as pharmaceutical products, foodstuffs, and other consumer products, involve particulates that are either compacted in the form of tablets, or supplied as powders, or reconstituted in solution. Construction materials involve slurries and cements and pastes. And finally, the energy sector, many battery electrodes are comprised of slurries, of electroactive particles suspended in a fluid. So these are just, this is not by no means an exhaustive list, but this is just some of the examples that we have in mind. So having motivated why we might care, let me define the what. So the what is classifying particulate media in liquids. Basically, this falls under two categories. So on the left is a fixed bed, so-called porous media flow. In this scenario, the particles are stationary and the liquid around the particles is mobile. And so as a result, you don't have to track the particle degrees of freedom. Those remain stationary. You only have to track the flow and any multiphysics coupling involved within the flow. The flow does interact with the particles, but you don't have to resolve the particle motion, and so you have fewer degrees of freedom to solve for. And this can be solved, as I'll discuss, at any scale, from the micro to the macro scale, and it's involved in a number of applications: reactors, chromatography columns, absorbers, heaters, and others. On the right, we have the scenario where the particles are dispersed in the liquid, and these are called suspensions. And the CFD terminology, we might call these multi-phase flows. And this is a considerably more complicated problem to solve, because now, in addition to solving for the fluid flow, you also have to capture the particle degrees of freedom as well. And the particles have their own momentum that can exchange with the fluid. The degree of that coupling between the fluid and the particle depends sensitively on the number, size, and mass of the particles. And as I discussed on the previous slide, these have numerous applications in a variety of products and industrial processes that are of import. So now that I've defined the why and the what, the how is next. And this comes to the topic of computational fluid dynamics and how we select a model for the particulate phase. The first thing one might do is, for a particular problem, you might ask how many particles are in the domain. So on the right here, I've shown essentially a schematic of jelly beans filled in the jar. The question is how many jelly beans are in the jar and whether or not they're countable and how crowded are they. This basically dictates the model that you might use in setting up a CFD simulation. So the parameter that you might calculate is the volume fraction, which is essentially a ratio of the total volume occupied by the particles relative to the total volume of the domain, and presumably the rest of the domain is occupied by a fluid, either a liquid or a gas. And so the subdivision of methods broadly is classified as to whether you have a very dilute system or a very dense system. In the former case, you would rely on, for a case where you have very dilute systems where the particles are countable in some ways, you might rely on discrete methods or continuum methods, depending on the degree of coupling between particles and the fluid. But once the particle density becomes very high and very crowded, using Lagrangian discrete methods becomes intractable at some point, and you have to rely on continuum methods to resolve the behavior of the material. And these can exploit so-called representative volume elements. These are essentially statistical representations of the microstructure. And that paradigm influences our modeling methodology. So we might often construct a microscale model of a countable number of particles in a system. This could be a fixed bed, or it could be a countable number of particles in a suspension. And the purpose of such microscale models is to calculate effective transport properties. And those transport properties are used in macroscopic models of the system. So these can involve, any of the different applications I described. The advantage of macroscale models is that you have reduced dimensionality relative to microscale models. The disadvantage is, of course, you lose information. And so the more accurate you have a microscale model and calibrating transport properties for use in the macroscale, the better and more accurate your macroscale model will be. So in the next few sections, I'm going to talk about some canonical cases, starting with fixed beds. So this, again, involves stationary particles with fluid moving around them. In subsequent sections, I'll talk about suspension flows. I see some questions in the chat already. Keep those coming. I will address those at the end after I've given the main webinar. But please keep them coming. So in fixed beds, there are a number of transport phenomena that are important. Even though we don't have to calculate the degrees of freedom in the particles influence the flow and transport. And so their presence obviously has significance. Some of the phenomena that we have to be aware of in fixed beds are shown here. So on the left is the phenomenon of hydrodynamics dispersion. So I'll describe this briefly. So this is the phenomena whereby a particulate microstructure has heterogeneity, and that heterogeneity gives rise to velocity heterogeneity. So you have fast-moving streamlines along linear paths in the microstructure relative to slower-moving streamlines that have to take tortuous paths along the microstructure. So very basically, you have fast-moving streams and slow-moving streams. If you suspend molecules in this fluid, those molecules will be dispersed at large scales. So some molecules will move ahead of others. Others will be trapped in stagnant regions or slow-moving regions. And as a result, on a macro scale, you have an apparent concentration gradient or apparent spreading. This looks like diffusion, but it's called dispersion. And so calibrating the dispersion depends sensitively, as you imagine, on not only the flow strength, but also the microstructure. The second topic to be aware of is the rate of mass transfer. So if you have molecules suspended in a flow and they're interacting with particles that are of a much larger size, the transport of molecules to or from the particle surfaces, again, depends sensitively on flow. The classical description, you have a strong flow flowing across a particle. The flow carries a solute. What forms is a concentration boundary layer. So in the bulk, far away from the particles, you have strong convection by the flow, but near the particle surfaces, the velocity is zero, and so you have this stagnant layer adjacent to the particles where solute now has to transport across it via diffusion. So this is a process whereby convection and diffusion are both important, both necessary to quantify the effective mass transfer rate. And this is important, as I'll describe, in a variety of applications, chromatography, lithium-ion batteries, and others. And finally, on the right here, I'm showing the pore mass transfer. So anything intraparticle, anything that depends on properties within the particle themselves, Convection is generally not important because the flow velocity within a particle is generally much smaller in speed relative to the interstices outside the particles. So when you're modeling poor mass transfer, generally you're only thinking about diffusion and any chemical reaction or absorption or desorption processes that are happening. Again, this is important in chromatography and also in lithium-ion batteries through lithium intercalation in the electroactive particles of a battery electrode. So how do we describe these phenomena? Well, the first two of those phenomena I mentioned depend on flow. The third does not. And so when you're describing these first two phenomena at the macro scale, generally it's intractable to model them at the micro scale, right? Because there's too many degrees of freedom. So instead, we rely on transport correlations. So on the left, is a description of the seminal work describing dispersion in fixed beds. On the right, I'm describing the seminal work describing film mass transfer. So the relevant, I know these slides are dense, but stay with me. The relative dimensionless group that characterizes the competition between convection and diffusion is called the Peclet number. And here it's defined with respect to the bed superficial velocity. That's just the flow rate divided by the cross-sectional area of the bed. And the larger the Peclet number, the more the dispersion. Right, so as you increase flow strength, the degree of velocity heterogeneity increases, and you get more dispersion. This topic was studied extensively by Howard Brenner, and then subsequently by John Brady and Don Koch at Caltech. And the relevant parameter to calculate is the dispersion coefficient. There's both a transverse and longitudinal dispersion coefficient. Here I'm showing the result for the longitudinal dispersion coefficient that was developed by Don Koch during his PhD thesis at Caltech. Valid at large Peclet numbers, you see that the dispersion coefficient correlates with the Peclet number and volume fraction, and this compares very favorably with experiments. You also have to quantify how the mass transfer rate of molecules disperse in the fluid to, how that transfer to particles depends on flow. So for that, the relevant quantity to calculate is the mass transfer coefficient, or in dimensionless terms, a Sherwood number. So this is the mass transfer rate divided by the diffusion rate. And for strong flows, mass transfer is substantially enhanced above the transfer rate that would be supplied by diffusion alone. And again, this depends on the Peclet number. So this correlation here from Wilson and Giannakopoulos is a classical correlation that's often used in chromatography modeling. The important scaling here is the Sherwood number scales with the Peclet number to the 1/3. That 1/3 scaling comes from an asymptotic analysis of the boundary layer and how it interacts with the flow. In addition, there's an additional complexity. In addition to flow, you can also have heterogeneous particle sizes, right? So given rise, you have a particle size distribution with some degree of polydispersity that can also influence mass transfer, as you might expect. So on the right here, I'm showing different particle size distributions. On the bottom are their relevant statistics. So 3 different distributions with different average diameters of spherical particles and different relative standard deviations or polydispersity indices. And these differences in microstructure give rise to differences in film mass transfer. The way that's computed is by integrating the mass transfer rate to the particle surfaces and normalizing by the probability of the particle volume within a given space. And so this integral, in the case of monodispersed distributions, reduces to this classical formulation, which basically is a mass transfer rate depends on mass transfer coefficient normalized by some geometric factor multiplied by a driving force, which is the concentration difference between the solute suspended in the or dispersed in the fluid relative to the concentration at the surface of the particles. And the final topic is pore mass transfer. Again, this does not depend on anything flow related. And so in lieu of correlations, we can actually use explicit modeling. So again, this has numerous applications in a variety of topics. But because convection is negligible in the particle phase, we can model concentration transport in the pore phase of the particles using partial differential equations. So the equation shown here is a diffusion adsorption equation. It depends on the particle porosity and the pore diffusivity within the particle, as well as this term here, the adsorbate concentration, which is governed by either the kinetics of desorption-adsorption or in the quasi-equilibrium case through an adsorption isotherm. So the most common one being the Langmuir isotherm. So the advantage here is we don't have any correlations. So we don't have to correlate how transport depends on any of these properties. We explicitly model it instead. The disadvantage is that now we've added extra dimensions to our problem. So in addition to solving for mass transfer of solute as a function of space and time, we also have to solve it as a function of particle size and intraparticle coordinate. So those particle-specific dimensions are shown here is a two-dimensional map. And so this becomes a very high-dimensional problem, right? So a fully three-dimensional problem becomes a five-dimensional problem. That's intractable. Typically, what you would do is simplify the dimensionality in space so that you can add these extra dimensions as a function of a reduced dimension in space. And this example is, this first example is one in which we do exactly that. So this is a macroscale model of a chromatography column. It's one-dimensional in space, but we've added extra dimensions along particle size as well as interparticle coordinates. What we're modeling is mass transfer of species injected to one end and basically tracking their degree of retention in the column, which depends on how the degree of affinity any molecular species have for particles in the column. And the question we'll ask is, how does particle size distribution impact important metrics for performance? Right, so I introduced these three distributions in a previous slide. The metrics for performance, there are various. The pressure drop and the retention and the efficiency are the most common ones. And again, we're simulating a variety of phenomena here, not just flow, but also particle-specific phenomena, film mass transfer and pore mass transfer, which are coupled to the flow. And the key result from that study, so I won't, for time, I can't show the extent of the study in full detail, but the main results are shown here. So on the left is the detected concentration as a function of time. The efficiency of the column is determined by the ratio between the retention time to the width of the base of the peak. So I'm showing four different molecules here. The width of the base of the peak is roughly 4 times the standard deviation. So it characterizes the extent of broadening of the signal detected at the outlet. The first thing to note is that if you change either the particle size, right? So, if you go from, say, A to C, or sorry, B to C, if you change particle size, that is accompanied by a drastic reduction in the pressure drop, as well as a reduction in the efficiency. Again, the efficiency is the ratio of retention time over the standard deviation of the band. If you increase polydispersity, this has an effect also, both reducing the pressure drop and reducing efficiency. It has a more significant effect on efficiency. On the pressure drop, the main factor of importance is the average size in the bed, not the size dispersity. That, isn't too surprising. And so for that reason, many chromatography beds are modeled using a monodisperse assumption, just characterizing the average size. But for cases where you have very heterogeneous particle microstructures, polydispersity becomes increasingly important. So cases where you have void spaces and the like. And so to summarize this first section, so I've introduced some important topics that will carry over in our discussion of suspensions. So first, the coupling between fluid phenomena and mass transfer phenomena to the particles. This gives rise to dispersion and mass transfer coupling. Both of those are important in suspensions as well. I've also introduced the concept of a size distribution. And so for stationary fixed beds, the size distribution does not change. For suspensions, as I'll show in the next section, this will not be the case. You have to actually solve for the size distribution function in the most general case as a function of particle size, but also in space and time. And so that leads us directly into the next section of the webinar, which is in suspensions. And I like to start with a classical diagram, which basically divides different regimes of suspension flows. So on the horizontal axis, I've already introduced the particle volume fraction phi. On the vertical axis, I'm introducing a second dimensionless number, which is the Stokes number. And this is basically a ratio of particle momentum relaxation time to the fluid momentum relaxation time, which for turbulent flows is characterized by the Kolmogorov time scale, or equivalently the Kolmogorov rate scale shown here. Depending on where you are in this parameter space of volume fraction and Stokes number, dictates the degree of couplings, both between the fluid and the particle, as well as the particles amongst themselves, and also choice of method. So on the left side, so for small volume fractions, are the case of dilute suspensions, which is the subject of this section. As you increase particle volume fractions, interparticle interactions become more and more important, and you have to start to account for not only how do particles influence the flow, which is the case of two-way coupling, but also in the most dense suspensions, how particles interact with each other and the flow, so-called four-way coupling. And each of these regimes correspond to different computational methods. So in this slide, I'm showing just some of the methods you might have heard of in the CFD literature. These correspond to different regimes in this regime diagram. So again, for present section, I'm going to be focused on dilute suspensions. And here I'm showing some of the phenomena that we might be interested in. So for dilute suspensions, I described that, for size distribution of particles, unlike in fixed beds, that size distribution may change. The phenomena that cause it to change are described by what's called the population balance equation. So the population balance equation is basically a conservation equation for the particle size distribution. So it's now a size distribution for both particle size and space. So it is units of inverse volume per particle size. So length raised to the -4. On the left are the typical transport phenomena you see in flow. So you have convection of probability and diffusion of probability. On the right are essentially source terms that govern in exchange between particle and the solute dissolved in the fluid and between particles. All right, so the first term is nucleation. So this is the phenomenon by which a solution, when quenched into the metastable region of its equilibrium, precipitates out into forming nucleates or crystals. This also applies in gas-liquid phenomena in the case of boiling. Nucleates in that case are gas bubbles. But once you have enough nuclei, those nuclei can continue to grow by mass transfer. So solute transports to the surface of the particles and absorbs, and that causes growth. Or in the case of undersaturated liquids, you can also have the opposite process of dissolution or evaporation. And finally, particles themselves can interact. So depending on the degree of fluctuations in the flow, particles might find each other and agglomerate, or if the flow is strong enough, they might break up. Right? So those processes of aggregation and breakup are interparticle processes, whereas growth and dissolution and nucleation are really interactions between single particles and solute. And because the suspension is dilute, these can be decoupled and treated separately. So here are some simple examples of evolving size distributions. So these are numerical calculations of the discretized population balance equation compared to classical analytical results in the literature. So the dashed lines are analytical results. The histograms are numerical results. What I'm plotting is the number fraction as a function of particle diameter. And these show how nucleation and growth and aggregation phenomena influence these size distributions under very specific conditions. So here I'm taking the rates to be constant. That's generally not the case. These are very simplified approximations, but in general show roughly how you would expect these distributions to evolve. To get more quantitative, we have to be more specific about these phenomena. So first, I'll describe nucleation and growth in a bit more detail. So again, this is an interaction between solute dissolved in solution, and when you change the conditions of that solution such that being dissolved no longer remains thermodynamically viable, and so they rapidly precipitate out and then grow. That precipitation event, where a solution is quenched into the metastable region of the phase diagram, is called nucleation. So here I'm showing an example that was taken from the Handbook of Industrial Crystallization. So this is the phase diagram of lysozyme, one of the most well-studied proteins, forms a rhombohedral crystal. And this red region I've highlighted here is the separation between the solubility line and the spinodal, which is the metastable region where nucleates form. The rate of nucleation is governed, well, in the earliest days was described by classical nucleation theory. That theory has been since revised in numerous contexts, and there are even phenomenological theories that have been added to make this theory more accurate. But the key insight is that the nucleation rate and the size of critical nuclei depends on interfacial energy between the crystal facets and the surrounding solution. So this interfacial energy has to be measured and used to calibrate nucleation rates and prototypical nucleate sizes. Once nuclei have formed, they can grow by continued absorption of solute onto the surfaces, but that is a mass transfer limited phenomenon. So if you model mass transfer limited growth kinetics, so this is the classical three-dimensional solution to the diffusion equation shown here, coupled by, if advection is present, so if you have convection by flow, you also have to modify the diffusion result by a parameter, the Sherwood number, which I introduced previously. So this Sherwood number depends on the flow. And again, because flow is a complex process that can couple to mass transfer, generally when we're modeling macroscopic phenomena, we use correlations to describe how the Sherwood number depends on flow strength. So again, we turn to correlations in the case of microscale phenomena that depend on flow in some way. And so here I'm showing correlations for growth and for aggregation. So on the left, this is very similar to the phenomena of film mass transfer in fixed beds. Here again, we have a correlation between Sherwood and Peckley numbers. The Peckley number is defined a bit differently here using the turbulent shear rate. This is equivalently the inverse Kolmogorov time scale to describe the rate of convection. The Sherwood number is not changed. Again, it's a dimensionless mass transfer coefficient. And the seminal work for mass transfer to small particles was done by George Batchelor. And the case of turbulent flows furnished the relation shown here. And again, you see the Peckley number raised to the power of 1/3. Again, that is a classical result that you saw in fixed beds, but it also see in suspensions, because the thickness of the boundary layer that is formed in a turbulent wake past particles is what dictates the rate of mass transport. And this is valid for very large values of the Peckley number, which is typically typical in many applications. On the right, I'm showing aggregation. So aggregation is a biparticle collision event, right? So the question to ask is, what is the probability that one particle will find another? And so that depends on the two particle probability distribution. And that can be mapped out at the microscale under different conditions. And the seminal works in this topic was first done by Smolkowski for the case of fluctuating particles in a stagnant fluid. So in that case, the probability that particles find each other is determined by Brownian motion and the degree of stabilization amongst the particles. Later, Philip Safman and Turner furnished a correlation for turbulent flows. So turbulent fluctuations can also enhance the probability of particles finding each other. And that leads to the relationship shown on the right, which tend to be very important in stirred tank vessels and other scenarios. Speaking of stirred tank vessels, this takes us to our first case study in this topic. So this is a case of protein crystallization via batch crystallization. So you have a stirred vessel containing a solution of dissolved protein that, in the scenario I'm going to illustrate, is quenched into the metastable regime of its phase diagram to induce nucleation and growth. The parameter I'm going to vary, which is dictated by molecular phenomena, is the degree of stabilization amongst the particles. So depending on whether or not you have electrostatic stabilization dictates whether or not aggregation matters. And that can have a very strong effect on the particle sizes formed in batch crystallization processes. So firstly, let's look at some of the flow characteristics in a stirred tank vessel. Right, so the flow characteristics, to get a little technical, depends on the second invariant of the velocity gradient tensor in the flow. If you normalize it, that basically provides a metric to determine whether or not the flow is dominated by rate of strain or by rotation, right? And why does this matter? So firstly, if we look at just how these regions are spatially discretized and segmented in the volume. So near the impeller, you have strong straining motion. Far from the impeller, you have strong vortical motion. And near walls, you have vorticity and rate of strain in approximate balance, which is basically a simple shear flow. Why does this matter? This matters because when you have particles suspended in the flow and now they interact in different flow fields, the degree of stretching of the boundary layers around the particles depends on flow type. Right, so in the literature, you might see different scenarios, different micro models for different flow types: simple shear, pure strain, rotation. The reason for that is that these different flow types can affect, in this case, mass transfer rates. Right, so the Sherwood number correlations that I showed before are flow type dependent. This can get exaggerated. So in the most general sense, for shear flow example, you can get interesting closed orbit phenomena where concentration boundary layers don't stretch. And so you have a much reduced extent of mass transfer when strain and vorticity are in balance. But in the case where you have rate of strain and vorticity along that strain field, you'll get stretched boundary layers, thinner boundary layers, and enhanced mass transfer. So now that I've described the flow characteristics, let's look at how the size distributions evolve in this stirred vessel. So here I'm showing a cool down process, typical batch. So this is a very simplified batch crystallization simulation where we have an initial induction stage where the solution is cooled rapidly into its metastable region where nuclei precipitate out of solution and then grow. After that induction period, the solution is warmed to a warmer temperature where they continue to grow and possibly aggregate. Depending on the degree of stabilization amongst the particles determines what size of particles you'll get. So in the case of strong aggregation or stability ratio equal to unity, you have strong thermal fluctuations and turbulent fluctuations that make the probability of particles finding each other much higher, more likely. And so this gives rise to very large particles at the end of your growth period. On the bottom, I'm showing the red curve where you have high degree of stabilization. And in that case, you have reduced particle size because now you've stabilized against aggregation. Particles tend to repel each other, and that gives rise to modified size distribution. So being a little bit more granular, we can look at the full distribution. We can plot this as a function of different stability ratios. Here I'm just showing the example for the highest stability ratio, so aggregation is suppressed. But very broadly, you can see, initially you have a very monodisperse suspension. This is immediately after the nucleation stage. And as time goes on, that distribution broadens in size due to growth phenomena. In the case where you have no electrostatic stabilization, so small values of that stability ratio, you would get an even broader size distribution and larger particles. I'll show another case study, and then I'll briefly talk about dense suspensions in the last section. So this case study is one that might be of interest to anybody in the combination products sector, which involves protein reconstitution. So this is a process that involves dissolution of particles. So you have a dual chamber auto-injector device, like the one shown on the top right here. These chambers contain one chamber contains liquid diluent. The other chamber contains a freeze-dried protein powder. And during an injection, the way these work is so there's a spring-activated piston that causes the plunger to push the diluent through the bypass channel and then rapidly mix with the powder, forming a reconstituted drug product solution that then gets injected. Highly concentrated injectables are becoming more prominent. And so therefore, one question that one might ask is, how long does this take? And what are the rate limiting steps? And so what simulation can offer is determining the time scales for dissolution, i.e. reconstitution, and how that depends on the typical sizes in the freeze-dried drug powder, as well as properties of the diluent. And so that's the topic for this case study. It's a complex process, right? We're only going to consider one step of the process. We're not going to consider any of the initial wetting and bond breaking and collapse, which occurs immediately after the liquid impregnates the freeze-dried drug powder. It's a porous media, but it's a dissolvable porous media. So as it wets, immediately dissolves and collapses. That's a very rapid phenomenon. We're also not going to consider the late stage process after dissolution, because that depends on whether you have mixing or not. So in the case where you have mixing, a solution can rehomogenize rather quickly, and that's a very vigorous flow. Without mixing, the rehomogenization can take much longer. We're going to only focus on these intermediate time scales, which can be rate limiting when you have very large particles, which involve really just dissolution and sedimentation. So here are the results from that simulation. So this is a population balance simulation. Coupling, two-way coupled, so bidirectionally coupled. The particles influence the flow because the particles have a size and mass that cause them to sediment. And so the flow that is produced is due to natural convection. Obviously, if you have external mixing involved, the natural convection that results is negligible, but what this shows is barring that degree of mixing, because mixing brings its own problems, can introduce gas bubbles and so forth. So if you have too much mixing, initially you can get inactivated drug product because proteins can absorb onto gas bubble surfaces. What this simulation shows is the stratification and density that results due to dissolution and sedimentation. So as the particles dissolve and the volume fraction shrinks, the solution enriches in dissolved solute. Concentration grows preferentially near the bottom because these particles sediment. So you get this heterogeneity that forms as a result of the sedimentation. That's captured by these plots here and made a bit more quantitative. So again, on the left, I'm showing the evolving size distribution. On the right is the solution concentration as a function of time. You see at long times, this concentration plateaus because you don't have external mixing. This disparity between enriched and diluted regions of the reconstituted liquid persists. The only way you rehomogenize these on timescales shorter than days is through external mixing. And then we can study how this depends on different properties of the diluent or the particles, right? So if you have depending on the freeze-dried drug product, which can be characterized by scanning electron microscopy or micro CT, you can get a variety of different size distributions, right? So here I'm showing examples for different final solution concentrations, which basically corresponds to different particle loadings. So same mean diameter, but different number densities of particles. So you're essentially increasing particle concentration. The particles are still dilute because the porosities of these lyophilized drug product cakes are very high. And what you see is that as you increase the solution concentration, viscosity increases exponentially, as does reconstitution time. And the reason for that is you're essentially limited by how long it takes to dissolve these particles until you get full reconstitution. And then there are other parameters we've played with. What happens if you have larger particles? Those tend to limit the reconstitution time. And so you have higher polydispersity, you'll also have longer reconstitution time because you're always limited by the largest particles. So I know that was a lot. I have one more section left to go, which I'll breeze through, but very briefly. So here I've introduced, we started with fixed beds where you have fixed size distributions. For suspensions, you have to solve for the size distribution as a function of space and time in the most general sense. This can be done with the population balance equation. Again, you have to consider microscale physics and use correlations where appropriate to understand how the microscale physics couples to flow, and that is then built in to macroscale problems of interest. So the examples I showed were batch crystallization of protein and protein reconstitution in dual chamber devices. So I have about 14 minutes left. So lastly, I'll talk about the last topic, which is dense suspension flows, and show one example relevant to drug delivery, and then I'll take questions. So again, I return to the regime diagram of Stokes number versus volume fraction. Here we are on the right here, where now we have a system where the particle-particle interactions are so numerous and the number of particles is so large that if you want to do Lagrangian particle tracking methods, that just becomes intractable. So typically people will rely on Eulerian methods and continuum methods, so-called two-fluid models and discrete element methods to model granular flows. Here, I'm going to show an example where the dense suspension is modeled as a homogenized fluid, but we have to characterize the material properties of that fluid. And this brings us to the topic of rheology. So any material that contains particulates or any constituents that span degree of length scales emits mechanical properties that ordinary simple liquids like water do not have. So I saw in the chat one example was blood. Blood is an example of complex liquid because suspended red blood cells and platelets can modify the response of the fluid to applied stresses. And this again depends on volume fraction, right? So in the context of blood flow, it's the hematocrit. For any suspension, you would call it a volume fraction. And different flow phenomena occur. Shear thickening and thinning, thixotropy and aging, yield stresses and paste. Toothpaste is an example of a yielding material. And you see these all around the house. So cornstarch and water is a canonical example of a dense suspension where, here is an example from the National Institute of Standards and Technology where cornstarch in liquid, if you shear it very gently, behaves like a liquid, but if you apply a strong force, it will act like a solid. That's called discontinuous shear thickening. Because you have very complex material property phenomena, these have to be calibrated by experimental measurements and also microscale models. So I introduced the concept of discontinuous shear thickening. Here is an example. This is taken from literature for cornstarch dissolved in a viscous solvent. And this is a plot of viscosity versus shear rate on a log-log scale. And the phenomenon I'm describing of discontinuous shear thickening is as you increase particle volume fraction, you start from, in the absence of particles, you have a Newtonian liquid, so something where the viscosity is constant with shear rate. But as you increase volume fraction and the particle interactions and collisions become dominant, and eventually you get to a stage where particle friction becomes important, this material behaves more like a granular material, and you see an abrupt change in viscosity as a function of shear rate. That's called discontinuous shear thickening. It still flows, but a much higher viscosity at higher shear rate, and the transition is abrupt. This has been studied extensively. It's still a topic of active research in academia. One of the most classical models is due to Mike Cates, the so-called Wire-Cates model, which is a modified form of the Krieger-Doherty relationship, if you're familiar with that, with suspensions. The main addendum to the Krieger-Doherty relationship is what volume fractions do the particles jam. It's called the jamming fraction, and it basically transitions between two states. In one state where the particle contacts are well lubricated, and the other state where the particle contacts are frictional, more like a granular material. And the degree of transition is controlled by the critical onset stress and this tuning parameter beta. And so this is a model that here I'm showing the dashed lines where we've calibrated that model to experimental data by fitting these parameters using nonlinear regression. And so using a model such as that, we can now solve flow problems involving dense suspension. So the example I'll touch on is an example very important in the pharmaceutical industry and the combination products industry, which is clogging in prefilled syringes. So I already mentioned that many combination products, the trend nowadays is turning towards highly concentrated injectables. The risk of that, obviously that has advantages. You can, inject at high dosage with shorter delivery times. It's very convenient. Problem is you increase the risk of clogging in prefilled syringes. And in suspension formulations of drug products, this absolutely becomes a problem because you can have a solution that behaves like a liquid suddenly turns into a granular material. So simulation can predict when that occurs and how properties of the material and properties of the design of the injection device affect the probability of clogging. So here's an example where we're looking at different suspension volume fractions using a continuum method, right? So you see that there are particles here. Those particles were added in post. They have nothing to do with the physics. I've just added them here for clarity. To highlight on the left, you're seeing a very dilute, or not a dilute, it's still a dense suspension, but a more dilute suspension. On the right, a very, very concentrated suspension, so 40% volume fraction. And you see, these are all run at the same injection force, but the injection speed can vary. And so as the main takeaway here is as you increase particle loading, you slow down for the same injection force, the suspension flows at a much reduced speed. You can quantify clogging in this way. So if you have a threshold speed for injection, below which essentially injection becomes dangerous, that is a failed product. That does not meet critical performance criteria for combination products. And 10 newtons of force, 10 to 20 newtons of force is a typical force that would be applied by a human's thumb depressing on a plunger. So what is the mechanism for clogging? So for suspensions, one mechanism is this phenomenon of discontinuous shear thickening. So again, this is the transition between lubricated and granular behavior. Again, the Wire-Cates model says that there is a critical onset stress. What determines that? It is determined by the interparticle interactions that matter, and also the bounding stresses in the system. And so for the prototypical fluid I showed, for glycerol water mixture with suspended cornstarch, we calibrated a critical onset stress of 5 pascals. That's not atypical. And if you look at the viscosity, if you plot the viscosity contours in the syringe, you see that the highest viscosities are observed near the entrance of the needle and in the needle, because the shear rates and the shear stresses are highest here. Beyond a critical onset stress, this is what gives rise to a sharp transition in viscosity. That's what leads to clogging. So now with that, we can use simulation to perform extensive parametric sweeps, right? So this is more like an exploded design of experiments, right? We can vary the particle loading, we can vary the needle gauge, we can vary the flow rate. And now instead of quantifying clogging by a threshold injection speed, we define it by a threshold injection force. This can vary, it's somewhat empirical. 20 newtons is a very common threshold that is used. And so if you look at this yellow isosurface, which corresponds to, and if you plot along the iso line for a volume fraction of 30%, this threshold determines clogging, right? So if you have needle gauges higher or equivalent needle diameters lower than this to the right of this line, or flow rates faster than this line, the force required to push the suspension through the needle increases and doesn't meet critical performance criteria. Right, so that could be defined as a clogged. Even though the suspension is technically flowing, the force required to cause it to flow is too high. So if you're, for at-home administration, not safe. And so I know I breezed through that. I wanted to highlight the importance of rheology in dense suspensions and how their rheology influences flow. I only touched on discontinuous shear thickening, but there are all kinds of flow phenomena, yielding, thixotropy, aging that can matter, and is important in a variety of flow contexts. So slurry formation, battery electrodes, cements, pastes, consumer products, many of these are dense suspensions, and you have to be aware of these phenomena in order to model them properly. Feel free to reach out to me via email. So I'll leave my email here for just a minute or two. So if you want to take it down, or you can contact us at contact@verist.com. Love to set up subsequent discussions. If you have interest in any of the topics here or any of the topics I introduced at the beginning of my presentation, love to hear more. So I'll wait a moment. Okay, all. Thanks for your attention. I'm ending the event now.